Let's take a closer look. Have you ever looked closely at a train wheel? You might think it's flat, just like a car tire, but it isn't. This little detail is one of the cleverest tricks in train design. Most people never notice it, but it's super important for keeping trains safe and speedy. Imagine if train wheels were flat. Would trains still run smoothly? Would they be able to take sharp turns or stay on the tracks at high speeds? These questions might sound simple, but the answers are rooted in smart science and engineering. Let's dig into how train wheels are shaped and why it matters. We'll use easy examples and clear pictures to show the difference. By the end, you'll see why this simple shape keeps entire trains rolling safely across continents. So get ready to discover the amazing science behind something as ordinary as a train wheel. You'll never look at trains the same way again. First, let's think about car tires. Car tires are flat and wide. This helps cars grip the road and turn corners without slipping. Cars can steer their front wheels left or right. This lets them follow winding roads easily. But trains are different. Their wheels don't steer. Instead, they are fixed straight ahead. Trains have to follow the steel rails below them. The wheels roll directly on the metal tracks, which means there's very little friction compared to rubber tires on a road. Now imagine if trains had flat wheels like cars. Whenever the train went around a bend, the wheels would rub hard against the rails. This would cause a loud screeching noise and make the train slow down. Over time, it would also damage the wheels and rails. So flat wheels just wouldn't work for trains. Engineers needed something smarter. This is where the magic of the conical design comes in. So, what does conical mean? You might have heard the word before, but let's break it down in a way that's easy to picture. Picture an ice cream cone. It's a familiar shape, narrow at the bottom, and gradually widening as you move up. If you slice through it, you'd see a slanted surface that gets wider at one end. That slant is what makes it conical. Now imagine wrapping that cone around in a circle to make a wheel. Instead of a flat disc, you'd have a wheel with a sloped surface all the way around. That's the basic idea behind a conical train wheel. It's not just a simple round shape, it's got a special angle built in. A train wheel isn't totally flat across its face. If you looked closely, you'd notice it's shaped more like a shallow cone. Instead, it's slightly sloped, wider on one side, narrower on the other. This subtle angle is easy to miss, but it's crucial for how trains work. This slope is called the taper or conicity. It's a small detail, but it makes a big difference in how the wheel interacts with the track. Usually, train wheels are tilted at about 1 in 20, which means for every 20 units across, they rise by 1 unit. This precise angle is carefully engineered for performance. Why make them this shape? It's not just for fun or looks. The conical design actually solves a lot of problems that trains face on the rails. This cone shape allows the wheel to roll smoothly on straight tracks and handle curves without slipping. It helps the train stay balanced and stable, even at high speeds. The wheel can automatically move a little left or right on the rail when the train needs it. This self-adjusting feature keeps the train centered and reduces wear on both the wheels and the tracks. This clever design is one of the reasons trains can travel so fast, even around sharp turns. Without the conical shape, trains would have a much harder time staying on track. It all starts with a simple cone. That little angle is the secret behind the smooth, safe, and speedy journeys we see every day. When a train goes around a corner, something tricky happens. It's not as simple as just following the tracks. There's a clever bit of engineering at play that keeps everything running smoothly. The outside rail forms a bigger loop than the inside rail. This means the path the train takes on the outside is longer than the path on the inside. That means the wheel on the outside has to travel a longer distance than the one on the inside. If both wheels spun at the same speed without any adjustment, something would have to give. But both wheels are stuck together on a single axle. They can't spin independently like the wheels on a car. So, how do they keep up? How does the train avoid slipping, screeching, or even derailing when it takes a curve? Here's where the conical shape helps. Train wheels aren't perfectly flat. They're shaped like a cone, wider on one side and narrower on the other. If the train shifts sideways on the tracks, the wheels roll on different parts of their cones. This happens naturally as the train enters a curve. The wheel on the outside of the curve rides on a wider part of the cone, which means it covers more distance with each rotation. Meanwhile, the inside wheel rides on a narrower part, so it covers less distance. This means the outside wheel covers more ground with each spin, perfectly matching the longer path it needs to travel. Just like it needs to on a curve, the train glides through the bend without any trouble. The inside wheel covers less ground, matching the shorter path on the inside rail. This clever design lets both wheels rotate together without slipping, screeching, or causing extra wear on the rails. It's a neat solution to a tough problem, and it's all thanks to the simple but effective shape of the wheels. Thanks to this design, trains can glide through turns smoothly and safely, even at high speeds or on tight bends. There's no need for fancy steering systems or separate motors for each wheel, like you might find in cars or other vehicles. The cone does all the work. It's a brilliant example of how a simple shape can solve a complex problem and keep trains running safely every day. Another amazing thing about conical wheels is the self-centering effect, a subtle but crucial feature that keeps trains running smoothly and safely. When a train shifts a little to one side, the cone shape of the wheels gently nudges it back to the middle, almost as if the train is correcting itself automatically. It's almost like magic, but it's really just geometry at work. Here's how it happens. Thanks to the clever design of the wheels, the train can maintain its path without any extra help. If the train starts to drift to the right wheel rides up onto a wider part of its cone, while the left wheel slides down onto a narrower part. This difference in diameter means the right wheel travels a slightly longer distance than the left, causing the train to gently steer itself back toward the center of the track. This makes the train want to turn back to the center, almost like an invisible hand guiding it back into place. The effect keeps repeating gently until the train is back in the sweet spot, ensuring a smooth and stable ride for everyone on board. This self-centering keeps the train perfectly aligned with the rails, even at high speeds or when traveling over uneven or bumpy sections of track. It's a vital safety feature that helps prevent accidents. It stops the train from wobbling or derailing, making sure that passengers and cargo arrive safely at their destinations. The wheels are always trying to stay balanced, without any computers or fancy controls, just pure mechanical genius at work. It's a simple solution that works beautifully, all because of the clever shape of the wheel. This design is a perfect example of how a small detail can make a huge difference in engineering. Engineers designed this over 150 years ago, and it's still used today. The self-centering effect is a timeless innovation that continues to keep trains safe and efficient, connecting people and places all around the world. If you look closely at a train wheel, you'll notice a thin lip or rim on the inside edge. This is called the flange. Many people think this part keeps the train on the tracks all the time, but that's not really true. The flange is actually just a backup. Under normal running, the conical shape handles all the steering and keeps the train centered. The flange only comes into play when something goes wrong, like if the train hits a sharp curve too fast or there's a sudden bump. When this happens, the wheel might slide sideways far enough for the flange to touch the rail. The flange acts like a safety barrier, stopping the train from jumping off the track. But if the flange rubs against the rail too much, it wears down quickly and makes a lot of noise, so the flange is there just in case. The real hero is the conical shape of the wheel, working quietly to keep the train rolling smoothly. Trains today travel at incredible speeds. Some bullet trains can go faster than 300 kilometers per hour. But with great speed comes great responsibility. Engineers have to make sure trains stay stable and passengers feel comfortable. If a wheel's conical shape is too steep, the train may wobble or hunt from side to side at high speeds. If it's too flat, the self-centering effect becomes weak, making it hard for trains to handle curves. It's a careful balancing act. That's why engineers test and adjust the taper of train wheels for each type of train and track. High-speed trains often use a slightly gentler cone to keep things smooth. Subway trains, which take sharper turns, may use a steeper cone for better handling. This balance between stability and comfort is always on an engineer's mind. Thanks to careful design, modern trains can be fast, safe, and smooth all at once. You can see the genius of conical wheels in action all around the world. Whether you're riding a city subway, a cross-country express, or a scenic mountain train, those special wheels are at work beneath your feet. For example, Japan's Shinkansen bullet trains use carefully designed conical wheels to zip safely along twisty tracks. Subway systems in London, New York, and Paris all rely on this same wheel shape to get millions of people where they need to go every day. Even heavy freight trains, carrying hundreds of tons of cargo, use conical wheels to handle sharp switches and long straightaways. The shape works for every type of train, big or small. Next time you see a train, remember, the special shape of its wheels is helping it move safely and smoothly. It's a neat trick you'll spot everywhere once you know what to look for. So, why aren't train wheels flat? It's all because a simple cone shape solves big problems. The conical design lets trains glide through curves, stay centered, and avoid slipping, all without fancy steering or complicated gadgets. This is a perfect example of how engineers use simple geometry to solve real-world challenges. By paying attention to the shape of a wheel, they made trains safer, faster, and more reliable for everyone. The next time you hear a train rumbling by, think of the quiet genius happening below: cones, curves, and a tiny flange, all working together to keep things on track. That's science in action, and it's everywhere once you know where to look. Thanks for joining this journey into the world of train wheels. Remember, sometimes the smartest solutions are also the simplest.